at some other graphs that we might see that might not fit the parabola, but still is related to what we're learning about with that. Let's look at how multiplying a function by a number is going to change the graph. Let's look for symmetry, and let's decide whether something's increasing, decreasing, or constant. So this is a little more laid back from the last section. A couple of things happen here with what we learned about parabolas. If the number in front of x squared is positive, the parabola does have that upward opening. But if they have a negative, it does have that downward opening. Then, if we change that and we multiply it by a number, we can see if it's going to be wider or skinnier. So, let's take a look at how that's going to be applied. Let's say we have a general shape, and we are going to reflect it about the x-axis. If a is less than 0, the graph is going to be reflected. So the number I'm multiplying by is negative. It's going to reflect it across the x-axis like a mirror. If the absolute value of a is greater than 1, not only is it going to do that, but it's going to stretch it vertically. So imagine taking a rubber band and stretching it vertically. It gets skinnier. If it's between 0 and 1, it's going to shrink it vertically. So imagine pushing that rubber band shut, it's going to get wider. So let's look at how this compares. How does 1/2 square root of x compare? Well, it's not negative, so it's not going to reflect it. It's between 0 and 1. So it's going to be that stretch, and we're going to see that it's going to be skinnier. Okay? So it's going to be shrunk because it's less than 1, and it's going to be getting skinnier by that shrinking method. How do we test for symmetry? When we're in our earlier grades, we fold the paper in half, right? So imagine you're taking all of these sketches and you're folding them in half. If something is symmetric, the left and the right are going to be identical, which means those coordinates are going to be identical, except that one is going to be the negative of the other. So if it's symmetric about the y-axis, the x-coordinate is the same but negative. Symmetric about the x-axis, the y-coordinate is the same but a negative number. So we say we replace x with negative x, and we get the same thing out. It's going to be symmetric about the y-axis. If we put a negative in front of y, then it's going to be symmetric about the x-axis. What does that actually look like, though? So to test for symmetry with respect to the x-axis, it's the opposite here like intercepts. I'm going to replace y with negative y. You always do it in parentheses. Negative y squared is the same as y squared. So I get the exact same thing back that I plugged in. So it's going to be symmetric to the x-axis. To test for the y-axis, you're going to do the opposite with the negative x. I'm going to plug that in, but oh wait, when I square it, I'm still going to have x squared. So this is actually symmetric to both. That does not happen often, guys. That's not a very common thing. So if I want to check for the x-axis, I'm plugging negative y in. Well, negative y squared is going to be y squared. But when I plug in that negative x, what happens? I'm not squaring it. It's different. So it's not going to be symmetric about the y-axis. So you're really only going to see that symmetry occurring when you have things like the squaring. So if I want to look for symmetry with respect to the origin, that's a slightly different scenario. If I am symmetric about the origin, the point negative x, negative y must be on the graph as well as x comma y. Look at this here. It's almost like if you folded it diagonally, like from corner to corner, with the sheet of paper, it would be symmetric, okay? So that's what you're thinking. Or almost like you're folding it down and then over. So it's kind of hard to visualize this unless you play with a sheet of paper and kind of get things going. So we're going to replace x and y with a negative and see what happens. Well, on the left, that's going to be a positive y squared. On the right, it's still going to be a negative. So it's not symmetric about the origin. There are very few functions that are symmetric about the origin. I'm going to replace here. And right off the bat, you know, x squared and y squared are happening, so it's probably going to be symmetric. And it is, because negative x squared is x squared, because we're plugging in those parentheses. Now, to test for symmetry, this is just kind of a quick graphic to tell you what to do. I suggest copying this down or taking a screen picture and printing it out and keeping it by you as you do your homework. It's just putting into a picture what I just said in words. You replace y with negative y to test symmetry about the x-axis. You replace x with negative x to test the symmetry about the y-axis. To test it about the origin, you're going to replace x with negative x and y with negative y. Let's look at if things are increasing or decreasing. So if something's increasing, the amount is going up, right? If your bank account is increasing, the balance is rising. If it's decreasing, the balance is dwindling or going down. And if it's constant, it just kind of remains flat. It's the same balance day after day after day. So let's look at this function. And I want to move from left to right, and I'm going to ride the graphs. It's like a roller coaster. So I'm going up. It's increasing. It's increasing. It's going up. It's increasing. Then right here at 1, it just goes flat. It's constant. And then I'm going down, which is decreasing, 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 all the way down. So when you're doing these, you're literally tracing that cursor over the graph and describing the behavior that you're seeing. So what does this mean? How can I put this into some sort of math language? Functions are increasing whenever they're headed up. So when x2 is bigger than x1, that tells you it's going up. When x2 is less than x1, it's telling you that it's going down. And when it's the same, it's constant. It's just a fancy way of saying when the graph is moving up, it's increasing. When the graph is moving down, it's decreasing. When it's staying the same, it's constant. So if I want to start determining the intervals where the function is increasing, decreasing, or constant, I can see that this is increasing because I'm riding from the left to the right. You're riding the function. It's going up. It's going to be increasing. Down, decreasing. Up, increasing. So it increases twice. Then, if I look at, I'm riding the function, I'm increasing, and I'm decreasing right here. So what do I describe that as? From negative 2. And so here's the other thing, guys. You always use the values on the x-axis to describe where it's increasing, where it's decreasing, or where it's constant. It's always the x values, which sometimes we get mixed up. So that's it, guys. That's as simple as this unit is.